In this simple truss problem, we've been asked to determine the force in each member of the truss and then to state if the members are in tension or compression. Going to use the method of joints to work this problem. And the first thing I'm going to do is look for zero force members, which the identification of which can make the problem simpler. It can simplify the problem if you have zero force members that you can ignore during the analysis. So if we remember from the lecture, I have two situations where I can have zero force members. The first is if there is a joint that has only two non-collinear members and there's no external load or support reaction at that joint, then those two members are zero force members. So I look at my truss and I do not see that situation. The joint where we could possibly have that would be at D or B. We have only two non-collinear members, but at D we have a 300-pound force present, and at B we have two non-collinear members, but we have a support reaction. So our first situation where we could have zero force members doesn't exist. The second situation we need to look for zero force members is where we have three members forming a truss joint and two of those members are collinear and there's no external load or reaction at that joint. So if we look at our truss again, joint C is of interest here. We have two collinear members, BC and DC, and there's no external reaction at that joint or an applied load. So by definition of zero force member, this member AC is a zero force member. That third non-collinear member coming into joint C is going to be a zero force member. So I'll write that on here sloppily. So we can ignore it in our analysis. Okay, so I've checked for zero force members, found one. I've hopefully simplified my analysis. Now the next thing I'm going to do is to draw a free body diagram of the entire truss so I can solve for the support reactions. So I'm going to draw a free body diagram here. And I'm going to label this point A, point D. I'll put point C on there, but I'm not going to show member AC since it is a zero force member. And here's B. And I'm going to show the 300-pound load acting vertically at D. And for the support reactions, I had a roller support at A. So I'm going to show an unknown force A sub x. Just going to assume it acts to the left. If I don't know which way it acts, I can assume it acts either way. And if I'm incorrect, I'll get a negative answer when I solve for that unknown. And B is a pinned connection, so I need to show B sub x and B sub y. Okay, and again, I just assume directions for those. And my dimensions here are, this is 3 feet, and this is 4 feet here. Okay. So I'm going to solve for the support reactions. I'll set up my standard reference coordinate system there, and I have 3 equations of equilibrium I can use, since this free body diagram is of the entire truss, which is a rigid body. So I'm just going to label this truss FBD. And I'm going to start by summing moments about A. I'm going to do this over here to save some room here. So if I sum moments about A, I'm going to have a positive 300 times 4 feet for the force at D, plus B sub x times 3 feet. A sub x and B sub y act through point A, so they don't create a moment about A. So I'll solve for bx. I get 3bx equals minus 1200, or bx equals minus 400 pounds. So since the answer came out negative, that means bx actually acts to the right. And I need to remember that when I draw a free body diagram of the pin at B when I start analyzing each joint. The second equation I'm going to write here for the entire truss is some of the forces in the y direction, and there's only 2 forces in the y direction, by, which I've shown as positive, and that 300 pound force, which is negative. So by equals 300 pounds. And now I'm going to sum forces in the x direction. And following my free body diagram, how I showed bx, b sub x, and the answer I got for b sub x. And again, this is something you may just do in your head, but I like to keep all the negative signs straight. So it's minus a minus 400, because b sub x acts in the, I showed b sub x acting in the negative x direction, and then I got a negative 400 for it, so it means it actually acts in the positive x direction. But those 2 negative signs take care of that and are consistent with my how I showed the force on the free body diagram. I showed a sub x acting in the negative direction. So when I solve this, I get ax equals 400 pounds. So a sub x acts to the left as I assumed, and b sub x actually acts to the right. Okay, so I have those for later. Now, using the method of joints, I'm going to go around the truss. I need to pick a joint to start with and go around and draw a free body diagram of that joint. Write the equations of equilibrium that apply to that free body diagram, and then solve for the unknowns at each joint. And I'll do that until, go joint to joint, until I know the stress, the force in each member of the truss, and whether those members are in tension or compression. So I'm going to start at point B. So if I look at this as sort of the truss, the entire truss finding the support reactions, that's sort of my solving step one. Now I'm going to go to point B for step two. I'm going to draw an FBD of the pin at B. So I'll say FBD of pin at B. Okay, so here's the pin. And now I need to show all the forces acting on that pin. So if I go back and look at the reaction forces caused by that support at B, I found that I had 400 pounds, B sub x was acting this way. B sub y was acting up. So those are known, and I have to show those in the directions that I've solved for. You can't, those are known forces now, so you can't just show the direction arbitrarily. It has to be in the consistent with what you found when you solved for the support reactions of the entire truss. And now the two unknowns here, I have F sub AB, which I know acts straight down. I'll call that F sub AB. And I have F sub CB, which acts in the direction defined by this slope triangle here. It's on a 3-4 slope triangle. And I'm going to use my standard reference system here. And notice that I assumed that both of the unknown forces in the members are acting in tension, that the members are in tension. And this is the recommended way for working these truss problems, whether you're using the method of joints or the method of sections, to always show an unknown in tension. And then if it's positive, that means tension. If it's negative, that means compression. It's just seems to be the best way to keep the negative sign straight. If you assume compression and then it comes out negative, then you have to remember that you assume compression, so it's actually in tension. If you always assume they're in tension, when you see a negative sign, that automatically tells you compression. If there's no negative sign, it's automatically tension. So I really recommend that, but I'll leave that up to you. Okay, now I have two equations of equilibrium I can use. Now remember, now we're doing 2D particle equilibrium with these pins, whereas with the entire truss, we were in 2D rigid body equilibrium, so we had that extra equation, the moment equation. Now we're back to some of the forces in the x direction equals 0, some of the forces in the y direction equals 0. So I'll sum forces in the x direction. I look at my free body diagram and my reference system, and I'm going to write minus 4/5 FCB plus 400 equals 0. Those are the only two forces in the x direction. And I find that FCB equals 500 pounds, and it's positive, so that means tension. Okay, so I've already found the force in one member of the truss. Now I'm going to sum forces in the y direction. And I have 300, positive 300, minus F sub AB minus 3/5 of FCB, which I determined was in tension. So it's acting down and to the left, so the y component of that is negative. And if I solve that for FAB, I get FAB equals 0. Okay. The third free body diagram I'm going to draw with and then apply equations of equilibrium to is the pin at C. So I'm going to say FBD of pin at C. And here's that pin. And I have a 500-pound force, which I just solved for, because CB, I said, is 500 pounds tension. So that means it's going to pull on A and pull on C. So FCB is 500 pounds. And I'm going to draw F. My unknown is FDC. And I'm not going to show the force associated with AC, because I already said that's a zero force member. It's 0. So I'm just going to ignore that. And here's where it's going to save you a little bit of time and trouble to alter your standard coordinate reference system. I'm going to put it along, I'm going to put the x-axis along the line of action of those forces, and that way I don't have to worry about any angles. And this may not be intuitive, but I think after you see it, it's, you'll say, okay, well that makes sense. So let's look at this. Now if I sum forces in the x direction, I have positive 500 minus FDC. So FDC equals 500 pounds tension, since it came out positive. And I mean, it just makes sense that there's only two forces there. The pin is in equilibrium, so therefore FDC has to be equal and opposite to the 500-pound force in in CB. Okay, so that leaves one pin. So I've solved for, so far, let's just keep track here. I've solved for FCB, I've solved for FDC, I've solved for FAB. I know that AC was a zero force member, so now all I have left is the member AD. So I'm going to draw my fourth free body diagram of the pin at D. That wasn't the right way to show that. It's not F sub BD, it is FBD. So step 4 here, or free body diagram for FBD of pin at D. So at D, I have an applied force or load of 300 pounds. I've got the unknown of FAD. I'm going to show that in tension. And then I've got the known force of FCD, which was 500 pounds tension. It means it's pulling on the joints at either end of it. And I know that that's on that 3-4 slope triangle. Okay, so FAD is in the x direction, so I'm going to sum forces in the x direction. And I'm going back to my regular XY coordinate system. I get FAD plus 500 times 4/5 equals 0. I solve for that and I get FAD equals negative 400. So right away I know that's in compression. And the way to show that is to rewrite it as a positive number and put a C after it. So FAD is 400 pounds compression. So FCB is 500 pounds tension. FAB is actually another zero force member. Now I don't think we could have deduced that from just applying the rules for zero force members. That's one where you're going to have to work through the problem, and it turned out to be a zero force member. FDC is 500 pounds tension and FAD is 400 pounds compression.